Good morning of the conference. Um, Apologies for a little delay this morning. We had some trouble to sort out with connections. This is one of the things that can happen in these online conferences, apparently. This morning, we are very happy to welcome Cyril Branciard for our plenary talk. Cyril is a CNRS researcher at the Institut Néel in Grenoble. And so Cyril is going to talk to us this morning about things that should interest many people in the QPL spectrum. So we've got quantum circuits with classical versus quantum control of causal orders. So I'll hand it over to Cyril.
Okay. Am I live?
Yes.
Yeah. Okay. All right. Good morning, afternoon, good evening, good night, everyone. Thanks for joining us. Sorry for the delay. Thanks for Shane for the introduction, and thanks to the organizers for giving me the chance to talk here, and for putting up this conference in this unusual format with all the unexpected things that can happen. So I will indeed talk to you about our work on quantum circuits with classical versus quantum control of causal orders. And this is joint work with Julian Vex, who is now a postdoc in Brussels, Alistair Abbott in Geneva, and Hippolyte Dourdan in Grenoble. All right, so given the audience here, I guess everyone knows what a quantum circuit is, but still I thought it could be useful to set up the stage. So here is what essentially everybody has in mind when talking about a quantum circuit. So we have a bunch of wires and a bunch of which represent some quantum systems. And we have a bunch of boxes which represent quantum operations that are performed on these quantum systems. So these quantum systems can be quantum systems living in some Hilbert space of any dimension, and those quantum operations are typically taken to be CP maps, completely positive maps, acting on some operators in some input Hilbert space, HAI for input, and outputting some other operator in this HAO for output Hilbert space. And these can act on single systems, or these can act jointly on several systems, and these operations could entangle quantum systems. So what such a circuit effectively does is it performs a global quantum operation from the past to the future of all the quantum systems. So here I'm denoting the past, or the whole quantum system living in the past in this Hilbert space HP, and it takes out a quantum system in this future Hilbert space. And so the effective result of the circuit is to implement this quantum operation from the past to the future. And now when we study such circuits, we may consider the case where some of the circuit operations are fixed by the architecture of the circuit, and some of those operations could be free to choose. So it could be free variables. And if we do that, then the effective global map from the past to the future just ends up being a function of those free operations that could be plugged into the circuit. So the resulting map from the past to the future is a function of those operations that we plug in. So it's a function of maps. It's a map that takes quantum maps to new maps, and that's what we call a quantum supermap. And we heard about that already quite a few times this week. So that's a nice way to understand and study quantum circuits. And now we may ask the question of, okay, what kind of quantum circuits can we encounter in quantum theory? So just as I depicted the circuit and the example in these first few slides, I was just showing circuits with a fixed causal order. So where all the operations happen in a fixed well-defined order, one after the others. And this is the standard model of quantum circuits, which has been studied in the last decade or even a few more years. And it has been studied in terms of quantum supermaps, or it's also called quantum comms or quantum strategies. That's essentially the standard paradigm when we talk about quantum circuits, or when we used to talk a few years ago about quantum circuits. But then we may ask the question of whether other more general quantum circuits could be allowed or could be built in the lab, or quantum circuits, or even more general quantum supermaps. And that was okay. So this is the set of all quantum circuits in a fixed causal order. But we know that we could imagine some other kinds of quantum circuits. So for instance, a classical switch. What is it? Just a quantum circuit where the order of two operations would depend on the value of a classical coin. So you could flip a coin and decide to apply A before B, or depending on the value, B before A, value of the coin. And I could have a classical switch in this way, and such a classical switch we can clearly be realized. Doesn't fit in the standard framework of quantum circuits. And then, of course, we can make this classical switch quantum, and we also heard quite a lot about this quantum switch, which has become quite famous. So essentially, the idea is to make this classical coin quantum, a quantum state, a quantum qubit here, and to coherently control the order between A and B. So clearly, in this landscape of quantum circuits, there's more to just the classical the quantum circuits with fixed causal order, and we may want to explore a little bit more this landscape. And one question that we may ask is, what is the most general quantum circuit, or even the most general quantum supermap that can be imagined? And that's essentially the idea behind this framework of process matrices. So Ognian Oreshkov, Fabio Costa, and Cyril Branciard a few years ago asked this question: what is the most general consistent supermap? And they showed how these could be represented as process matrices. And so the idea would be to have a quantum supermap that doesn't a priori assume a well-defined order between the operations. And indeed, they found that in this generalized framework, we could have situations where the maps ABC are not used in a well-defined order, and this can give rise to situations that are called causally non-separable process matrices, where you cannot embed the operations inside the circuit or inside the supermap in any well-defined causal order, and that can also give rise to non-causal correlations, which is a kind of device-independent version of this causal non-separability. Okay, so this was a kind of top-down approach where you allow for the most general supermaps. Here in this work, we were trying to take a bottom-up approach. So we try to consider all the circuits that we could envisage and that we could possibly build in the lab. So we know that the classical switch, the quantum switch, are circuits that could be realized. So we asked the question of what else can we have in this landscape of quantum circuits. And the result is that we define a new class here of quantum circuits with classical control of causal order, which, as a standard example, includes the classical switch, and this larger class of quantum circuit with quantum control of causal order, which includes this quantum switch. And this essentially defines the outline of my talk. So I will first remind you how we analyze quantum circuits with fixed causal order, which I would call QCFO for fixed order. How we analyze this in terms of supermaps and process matrices. And then I will introduce those two new classes of quantum circuits with classical control, QCCC, and the quantum circuits with quantum control, QCQC here. All right, so for the fixed order case, so that was the figure that I showed before. So we have these operations ABC, which happen in a fixed order in the circuit, and any such circuit with a fixed order can always be realized in such a way. So by putting all these three operations in a well-defined order, so it could be in parallel, but it's just equivalent to consider them in a well-defined order like this. And what the circuit does is it connects all those three operations, possibly through using ancillary systems as quantum memories. So in this picture, we have those three operations, which can be any CP map, which I will call the external circuit operations. And inside the circuit, there are those fixed operations, M1, M2, N plus 1, which here I will consider deterministic circuits, so which here will be CP-TP maps, trace preserving maps. I could also generalize that, but for now, we'll consider that these are deterministic operations inside the circuit. So now to analyze the supermap that is obtained from such a circuit, what we do, well, in order to obtain the global induced map from the past to the future, we just have to compose all the operations in the fixed order. So M1, then A2, M2, A2, up to the end. And now to go further with the technical details, what we do, and I think I will skip that. We introduce the Choi isomorphism just to represent any CP map as a matrix, a positive semi-definite matrix. Then this composition of maps can be written as in terms of a specific particular product on those matrices. I'll go fast. So essentially, this Choi isomorphism allows us to write this composition of maps in terms of just a product of those Choi matrices representing each operation. This so-called link product is commutative and associative if you define it properly. So you can rewrite this product in this form. You just reorder the terms, and here you get so you separate the internal circuit operations from the external ones, the three operations. And so you get the global input induced map M as a function of the product of all the operations that you plug in, and this term here, which we call W, and here it is, and which is what we call a process matrix. Okay, so all the information that is inside the circuit, inside this pinky salmon circuit, all these operations are encoded somehow into this process matrix. At least all the information that you need to know to obtain the global induced map M is in this process matrix. So, and in this case, the way it was introduced, it was called a quantum comb, which is just a process matrix where the circuit has a well-defined causal order. Okay. So yeah, as I was saying, this contains all the information that you need to know about the internal operations to compute the global map from the past to the future. So you can then just forget about the what's inside the circuits. Just need to know this W. What is nice is that you can characterize the set of all such Ws. And in this case, for fixed causal order, it's just a simple causality condition that gives you a specific constraint on this W, which I will not go too much into the details. But essentially that gives you some constraints, which is nice, is that these can be written as SDP constraints, semi-definite programming constraints. So these can be checked efficiently, and you can characterize in principle efficiently the whole set of quantum circuits with fixed causal order. What is it good for? Well, for instance, if you have a a specific task that you want the quantum circuit to realize, then once you have characterized the whole class of circuits that you may allow, then you can try to optimize for certain tasks. So it's good to have a characterization of such classes, and a simple characterization, so that you can characterize. You can check if a given W is in this class, and you can optimize for certain tasks if you want. Okay, so that's essentially setting up the stage for quantum circuits with fixed causal order, and now we want to go beyond this. So first step beyond this fixed causal order paradigm is to introduce some classical control, which is what I present now. So basically, the canonical example is this classical switch, where instead of having either this or that in a fixed order, then you may want to include some coin inside that decides whether it's A or B first and B or A that comes second. So the way we propose to do it is as follows. So we keep this teeth structure for the circuit. We have some empty slots where we will plug in the operations, the free external operations that we want to use in the circuit. But we don't define a priori which operation goes where. So we have this bunch of operations that we want to plug in, but we don't know yet where to plug them in. And it's actually the circuit, as we will use it, that will tell us which operation to plug and where. So as we use the circuit, there will be this first internal operation, which is no longer just a CP-TP map, but which will output some value of some parameters, which will tell us which operation to use and to plug into this first time slot. And then we use the circuit again. There's this second internal operation that tells us which operation to plug in at the second time step, and so on. And all the operations, all the internal operations of the circuit tell us which of the boxes that we have at hand to plug in and where and when. And in this way, so those internal operations control the causal order between these operations in a classical way, because these are well-defined classical values that are spit out by the internal operations. So before, in the fixed order case, we had CP-TP maps, deterministic maps inside here, those internal operations. Now, so we relax this assumption of CP-TP. They're not trace preserving. Each of them is not trace preserving anymore. Then they have some output, and what we ask for now, since we still want some deterministic overall transformation, we still ask these to sum to CP-TP maps. So it's quantum instruments, if you're familiar with this language. So this is how we propose to describe quantum circuits with classical control of causal order. So as I was describing, there's a classical control here that determines which operation comes next. One crucial assumption here is that we started with n free operations at hand that we want to plug into the circuit. So one crucial assumption is that each operation should be applied at the end of the circuit once and only once. And this is because we want to define a proper quantum supermap. So we still want to have this linearity property. So we want the global map to depend linearly on those external operations. So we impose that each operation is applied once and only once for this purpose. And as we saw, so then the global order is not fixed a priori, but it's established as we use the circuit. It's established and recorded on the fly. And I didn't insist, but each internal operation here depends on which previous operations were applied before. So in this way, we can have some dynamical causal order in this with this construction. So now we want to describe it in this process matrix formalism. So let's see how to describe this whole circuit as a process matrix. So if we remember the fixed order case, we just had this star product of all the internal operations that define the process matrix of the circuit. Now, in order to obtain the process matrix of this circuit with classical control, now instead of the previous internal CP maps, we have those CP maps here. Okay, and we still take the link product in the same way. So we obtain such a term which corresponds somehow to the order being K1, K2, K3 up to Kn. But of course, all the possible orders could be obtained. So to obtain the process matrix, what we do, we don't want to post-select on a specific order, so we just sum all those possible orders, and that gives us the process matrix of such a circuit. So again, once we have the process matrix, we can forget about the internal structure of the circuit, and actually different possible realizations of the circuit may exist for the same process matrix. What's good is we just need now the W matrix to analyze and to know the globally induced map. And as before, we had this characterization of quantum circuits with a fixed causal order, which were written in terms of SDP constraints. So what is nice is that here, also for this class of quantum circuits with classical control, we still have a nice, well, maybe not so nice, but we still have a SDP characterization. So we can check efficiently whether a given W is from this class, can be realized as a quantum circuit with classical control. And we could, for instance, use this characterization to optimize certain tasks. So if I'm giving you some tasks that you want to realize, and I'm telling you, okay, you can use quantum circuits with classical control, then you can try to optimize the circuit that will realize the given map. And also with such a characterization, it's an if and only if condition, and we have a constructive way for any given W that satisfies all those constraints. We know how to construct a particular way, a particular circuit that realizes the given W. All right, so that was for the case of quantum circuits with classical control, the first step beyond the fixed order situation. Yeah, maybe just a few more words. What we get here, for those who know about this process matrix formalism, is only causally separable process matrices. And actually, we can see that it's just a mixture of different terms corresponding to different orders. So each of them is not necessarily a valid process matrix, which is what allows for dynamical order, but the sum is a valid. And because of this structure here, we only end up with causally separable processes, as we would have expected. All right, so now the second step is to go to now a quantum control of causal order. Again, the canonical example is from the classical switch. We want to make it quantum, so we change the classical bit into a quantum bit, and we allow for superposition and for a coherent way to control the order of the operations. So the way we do it is essentially to make the classical control we had here quantum. How to do that exactly is we do it as follows. So first, in order to make something quantum, we need to embed it into a physical system. So the first thing to do is to encode this classical control into a classical system that flies through the circuit here, with the given classical states that encode the causal order, and which controls which operations are applied at each time step. And of course, once we have this description, then we can just make this control quantum. So this double line that was representing a classical system becomes a single line. We just make it quantum. There are a few tricks here. So first thing to notice is that we actually make all these operations coherent. So here we were just using some kind of incoherent description of CP maps. Here we make the operations coherent. Essentially, that these would correspond to the cross operators of the CP maps that we used as a representation before. And now what's important is that this control, which before was encoding the whole causal order that was being established as the circuit was being used, this control now only records which operations have been applied already, but not their order. So here we only record with this control the unordered set of which operations have been applied before. So the reason we record this is that we still have this assumption that each operation should be applied once and only once. So we still need this control to remember something about which operations have been applied already, but we don't want to record everything. We just need the unordered set. And indeed, this is what allows for different orders to now interfere. And this is what allows us to get some real quantum control, and in particular to obtain, in some cases, some causally non-separable processes, just like the quantum switch. So again, in this framework, we want to describe such a quantum circuit with quantum control in terms of a W matrix. So if we remember the previous case of a quantum circuit with classical control, we had this incoherent sum of different terms corresponding to different orders. And now the way we can obtain the process matrix here is, instead of having an incoherent sum, to have a coherent superposition of different terms corresponding to the different orders. So here, this is the Choi representation of these pure operations. So instead of the CP maps, we have essentially the cross operation, the cross operators, and the Choi representation. We can still define a link product for the Choi representation of these, and now we have a coherent superposition of these, which give us the process matrix in such a way. So after tracing possibly some ancilla at the end. And again, we can tell the same story. So we only need to know the W matrix to analyze this circuit, and the same different circuits may have the same W matrix. So a given W matrix may have different realizations, and we again have a nice characterization of this class of quantum circuits with quantum control as SDP constraints again. So which is nice. Once again, if we want to optimize some tasks, if we want to check whether a given W matrix is in this class or not. And again, we have a constructive way, given the W matrix, which does satisfy this characterization, we have a constructive way to obtain the corresponding circuit in a non-unique way, that we can give the operations to plug in or to compose in this way to obtain the circuit. So just a quick word on possible realizations of such a circuit. So what we have in mind is a kind of situation where we would have the different boxes, and this is really inspired by the possible realizations of the quantum switch. So we would have the different boxes there, and we would send maybe a particle in a superposition of the different on the different path. And then between each time slot here, we'd have the circuit that would route back the particle to the right positions there, possibly in a superposition, and also applying at the same time those internal operations. So in such a case, the control states, which would just be the path of the particle, and some other degree of freedom, which would be used to record which operations have been applied before. And again, the circuit should root the particle and apply the internal operations as well. So since these internal operations depend on are not the same along the circuit, so these would need to be time dependent, or we could use another physical system that encodes a timer that gets incremented. So that's for possible realizations. Now I will come back to this this example of the quantum switch to check that this can fit in the framework. So that's what you all know. We have a particle that goes through the circuit depending on the value of the control qubit. It goes to A or B first, or in a superposition. Just a few words to say that it has been realized experimentally in quite a few experiments now. So how does it fit in our description? Well, we can precisely identify those internal circuit operations. So this one would just be the operation that prepares the quantum state of the target system and sends it to the right operation to be applied. And then this other operation would just be would just correspond to the identity channels that are used to send the particle from the output of A to the input of B, and for the other one. And then this one is the identity channel that takes the particle to the output there, and that records the control qubit and sends it to this control system. And if we describe it like this, then indeed we obtain the W matrix, just as I described before in the talk, and we get exactly what was written before when the quantum switch was analyzed in the process matrix formalism. Okay, that's a possible realization of the quantum switch. We can identify here how these operations are encoded. Maybe I will go quickly on that. Essentially, we can identify this control system that I was using, which is here encoded into the polarization and path. And in our description, this system actually only needs to be two-dimensional. So we realize that somehow in this particular implementation of the switch, there's some redundancy on how the control is encoded. So this already led us to propose some new possible implementations of the switch, which doesn't use so many degrees of freedom, but which is at the cost of being time dependent. So I will skip that. We can still make it time independent. Maybe something more interesting is that in this class of quantum circuits with quantum control of orders, we have some new examples of such circuits, new examples that may be of particular interest beyond the quantum switch. So here's one particular example. So just to clarify, it's a circuit with three operations. I just kind of unfolded it here to represent it, but really we should imagine that those operations are applied and the circuit loops back to ABC. So it's only three operations in this way. And what's interesting here is that these act on some target system, and the target system gets somehow copied onto the polarization, which will decide via these polarizing beam splitters which operation will come next. So really the operation of A, so which operation we plug in here, will affect the order of the upcoming operations B and C. Right. So in this way, we really have some dynamical causal order, not only dynamical here, but also coherently controlled. So we have both coherent control and dynamical order with this particular circuit. And what's nice also is that you get something causally non-separable, even if you trace out whatever control system you get at the end. So with the quantum switch, when you trace out the control system at the end, it becomes all causally separable. You don't get any. I mean, it's still compatible with a well-defined order if you trace out the control at the end. And here you can still trace out the control and still be causally non-separable with this dynamical and coherently controlled causal order. I will go very quickly on the applications. So as I was saying, I didn't say that the quantum switch, for instance, allows for new applications in for quantum information processing, and the best known application may be to discriminate between commuting and anti-commuting operations. So we know that there are things that we can do with quantum circuits that go beyond the standard framework. And so typically these are, since those circuits are seen as supermaps or higher order operations, we would look for applications for kind of higher order QIP tasks, so which compute functions of maps. So here are a few examples. All right, given the time, I will also go very quick, but we do have an example where for a given task, where we have to identify some unknown unitary, then we get a clear separation between the probability of success when you use a circuit that only uses the operations in parallel, in fixed order, or with this classical control, or clear separation with the quantum control, and even with the more general Ws. One natural question is whether we can violate causal inequalities with our new quantum circuits with quantum control, and this was actually one of the main motivations for this work, to really see. We know that the quantum switch doesn't allow for violation of causal inequalities. We were trying to get circuits which would violate causal inequalities, but unfortunately that's not the case. So we can prove that this particular structure for this characterization of quantum circuits with quantum control imposes some strong constraints on the correlations, and in particular that these correlations are causal. So no hope to get causal inequality violations, unfortunately. All right, so just to sum up, I described new classes of quantum circuits seen as quantum supermaps. So with the fixed causal order, which is the standard, described a whole new class of classical control and of quantum control, which can give causally non-separable processes. I should just mention that there are some other classes that have been identified in the literature. So for instance, in this paper, Matheus Araújo proposed a way to distinguish what they call purifiable process matrices, which is still a class that is a bit larger than our quantum circuits with quantum control. And in that paper, they argue that these might be the physical ones. So there might still be a gap between what we could imagine here and the possibly physical process matrices. So the main message here is that we have some new types of quantum processes with indefinite causal order that we can play with. So far, most of the studies were focused on the quantum switch or straightforward generalizations of the quantum switch, and here we really have more to play with this dynamical order in particular. So we can look for new applications. Okay, some people may be interested in possible different implementations of those circuits. So we know that the quantum switch has been analyzed, and there were proposals for gravitational versions or gravitational realizations of the quantum switch. So it may be an interesting question to look at. And there's still this question of, okay, we still don't reach the whole set of process matrices. So there are still some process matrices which are valid in the framework, which are not in this class of quantum control. So it's still an open question what they may look like physically, and whether we could imagine some realizations that violate causal inequalities. So I will stop here. Thank you very much. Thanks.
Yeah, only I can clap, but the claps take place over on Slack. There are many
thanks.
already. Thank you, Cyril, for a very nice, very pedagogical talk. That's you got some lively commenting over on Slack as the thing was going on. So maybe some people want to ask some questions afterwards as well. But go through some questions that came up going through the talk. So a question that came up early on from John van de Vettering was, I mean, a comment, I think more than a question, but just wondering why all the focus on quantum switches in this kind of work. So I think in the later slides you got onto things beyond quantum switches, but do you want to comment on why people talk so much about quantum switches and maybe relatively little about other?
Yeah, well, that was kind of the motivation of our work. So indeed, we know that we could imagine some quantum circuits with indefinite causal order, and the first thing that comes in mind is this quantum switch. So many people indeed focused on that. And we asked, okay, what is beyond the quantum switch? Can we imagine some more general situations where we would have some kind of superposition of causal orders or temporal orders, whatever you call them? Is there something else different from the quantum switch that we could imagine and that could be useful and could be fun to play with and that could find some nice applications? So this was really one of the motivations. We also knew that the quantum switch doesn't violate any causal inequalities. So we read this proof earlier, and we knew that this could also be applied to some of the natural generalizations of the quantum switch. And we really wanted to know if everything that was somehow quantum controlled would also fail to violate causal inequalities, and that was the case.
I see. So that maybe relates to another question that came up from Alexei Grimbaum. So he's asking, I think before you said it in the talk, whether these QC process matrices, is it true that they cannot violate a causal inequality? I think you've said that yes.
Yeah.
And then is this the point of distinguishing them from all other process matrices? Is the question, I guess.
The point of distinguishing them?
The fact that they cannot violate causal inequalities. Is this?
So in this work, our hope was really to kind of imagine new types of processes which may be able to violate causal inequalities. So we really didn't know from the start what was the limiting thing and why the quantum switch didn't violate causal inequalities, what would be needed to go beyond and allow for violations. So we imagined those new classes, and then we analyzed them, and then we tried to see if they could possibly violate causal inequalities, and the answer was unfortunately somehow negative. So the point is that there's still something to explore beyond our class of quantum processes with quantum control. So we characterize a new class that we would know how to realize in the lab. But yeah, that's just the limit of our imagination. We don't know what's beyond. We'd like to be able to know how to construct other types of process matrices, but we don't know.
Okay. Alexei also asks, can we build experimentally a system that mixes coherent and dynamic controls in your terminology? So
yes, that was precisely the proposal and the example that I was presenting. So yeah, we have ideas on how to implement those, and if there's any experimentalist that is listening to us that got lost and is here, yeah, that's a challenge for them to realize new types of such processes beyond, again, the quantum switch, which would demonstrate coherent control and dynamical control. That would be quite nice.
Right. Looking forward to the experimentalist responses on that.
Yeah, just
okay, so another couple of questions that came up. going through the slides. So I think around slides 13 to 15 or something. So John van de Wettering again. So he asks about the star products that you're using on slide 15. So he asks whether this is bilinear, and in that case, does that mean that that the big sum that you've written can actually be brought into the individual m's by bilinearity of this star product?
So it is perfectly linear or bilinear, but no. Then so the sum can't be reduced, and we cannot take just individual sums for each term, because essentially here, so that this first one would depend on K1 only, but this last operation depends on the whole order of the operations that were applied before.
Okay, I see.
So we just have one global sum, and sums over indices that are used once and only once. Okay. So it's just a sum on the permutations, not on the individual indices.
I see. Okay, and around the same point, Timothée Ouvremont was asking if the object defined on these slides on 13 to 15, if this is equivalent to a sum of probabilistic quantum combs with different causal orders, or is it something more than that?
Yeah, that's it exactly. Yes. Okay. So indeed, I was saying that I wanted those operations for the quantum case to be trace preserving. I could also generalize this, and that's one generalization of this. So where these are probabilistic operations, which give rise to this dynamical order.
Okay, all right. So let's see. Let's go through. So Lydia Del Rio asks, do you know if there's any complexity difference between QCFO and QCCC? Fixed order and the classical control.
In terms of computational complexity, or?
Yes.
No, I'm not sure how to answer the question. Yeah, so we just have examples where there is a gap for some specific task and for some specific number of operations where there is a gap between some maybe some probability of success or some fidelity at realizing some task. We didn't translate that into any asymptotical complexity or something. No.
Okay. All right, so a question from Alex Kissinger. Is it possible to give a fixed generating set for the quantum-controlled quantum circuits, for example, with systems of a fixed dimension like qubits, maybe after closing under composition?
So you mean to try to build any such circuit only with qubits?
So he's saying if you take if you make an assumption that you're working with systems of a fixed dimension, like say qubits, could it be possible to give a fixed generating set from which you could compose to build all of the quantum controlled quantum circuits? I hope I'm phrasing this right. It's a difficult task sometimes reading people's questions, but I think that's...
Yeah, I'm also not sure I fully understand the question, but...
Okay, so maybe for one like this, it's kind of most useful to hop over onto the Slack to follow that up. Okay. So Alex follows up with that. He says like a universal set of gates, basically.
Yeah, so
QC,
no,
QC.
I wouldn't think so, but I didn't think about that.
Okay. He also asks, is there a known example of a process matrix that at the same time doesn't violate causal inequalities and is not in QC?
Huh. I guess the short answer is no. I'm not aware of any such example. Well, It might be quite possible to build such an example if you take for instance the first process matrix introduced by OCB, Oreshkov-Costa, and Bruckner, and you add some noise. At some point, it will stop violating a causal inequality. But I'm guessing that the point at which it enters this QC class would be lower. So there might be a gap where it stops violating any causal inequality, and before it enters the set. But now the question of whether a process matrix like this violates a causal inequality in general, it's not such an easy question, because you need to consider any possible scenario with any possible number of inputs and outputs, and you essentially need to construct a causal model for that.
So maybe one final question. So Lair Christiansen, he asks, so since the internal operations, the M's of the controlled supermap depend on the classical label for the possible inputs, he's wondering what does the overall input channel, the cone, what does this look like? Input channel or cone?
Sorry, I missed the question.
So Larry is saying that since the internal operations of the supermap depend on these classical labels, now he's wondering what the input channel that you feed into this looks like.
Well, so in this case, that could be any quantum input. It's those internal operations that define these outputs, and in that case, with the classical control, it only appears here when we encode this control into some physical system, classical system here, along this line. But there's nothing a priori or in full generality there. There's nothing that is fed into the circuit that would encode the order. Of course, you can encode some order in this system here, but it doesn't have to be there.
Okay, all right. So that's already quite a lot of questions. So maybe at this point we'll let the discussion flow on.
Yeah, I'm happy to continue answering questions. Yeah.
Okay, so we can thank Cyril again for a fantastic talk and for being very patient with questions. So
okay, thank you very much.
Nobody else can, but everybody is welcome to clap over on the Slack. Thanks again, Cyril.
Bye.
Okay, guys, are we offline at this